Welcome, everyone. Today we're going to dive into something called automata theory. And I know it sounds super academic, but stick with me, because it's actually the fundamental rule book for computation. It's the simple, elegant logic that lets a computer do things like understand language, spot patterns, and make decisions, all by looking at just one symbol at a time.
All right, so here's what we've got on tap. First, we'll lay down the basic rules. Then, we'll build this fascinating little machine that has, get this, amnesia. We'll see what it can do, what it can't do, and finally, where it fits into the grand scheme of things, what we'll call the ladder of computation.
Okay, so let's start with a question you've probably never thought to ask. You type an email address into a form, and almost instantly it tells you if it's valid or not. How does it know? It feels like magic, right? But it's not. It's actually all based on a set of incredibly simple rules.
And I'm not kidding. These rules are everywhere. They're the secret sauce in the compilers that turn our code into software. They power the find and replace in your text editor. And they're even a core concept in huge fields like AI and bioinformatics. This stuff is fundamental.
So to really get how all this works, we need to speak the same language. And I don't mean English or Spanish. I mean the language of computation itself. Let's get our basic terms straight.
It all boils down to three really simple ideas. First, you've got an alphabet. That's just a set of symbols, like, say, the letters A and B. Next, you take those symbols and make a string, which is just a sequence of them, something like A, bay. And finally, a language is just a collection of strings that we decide we care about. For example, our language could be all the strings that happen to end with the letter A. Simple, right?
Okay, now for the fun part. Let's actually build a machine that can recognize one of these languages. We're going to start with the most basic version you can imagine, a machine with one huge weakness. It has absolutely no memory of what it's already seen. We'll call it the machine with amnesia.
So this little guy is called a deterministic finite automaton, or DFA for short. This is our machine with amnesia. Think of it like a board game. It hops from one circle or state to another based on the symbol it reads. And if it lands on one of the special final states, the ones with the double circle, when the input runs out, it basically gives a thumbs up and says, yep, I accept the string.
Let's actually watch it in action. We'll feed it the string Baba. Now, this machine's job is to accept any string that ends with an A. So it starts at the beginning, it reads a B and stays put. Then it reads an A, and yes, it moves to that final state. But wait, then it reads another B and gets knocked back to the start. But that last A, that's the key. It sends it right back to the final state just as the string runs out. And success! The string is accepted.
Okay, this looks a little scary, but it's just the formal way of describing what we just saw. The really important part here is that little delta symbol, the delta. That's the machine's brain, its rulebook. And notice what its rules depend on. Only two things, the state it's in right now and the one single symbol it's looking at. It has no idea what came before. That, right there, is the source of its amnesia.
All right, so that's our basic machine. Pretty simple. But what if we decided to tweak the rules a little bit? What if we gave our little automaton a kind of superpower?
This is where it gets kind of wild. Instead of being stuck in just one state at a time, what if the machine could split itself? Like it could explore multiple paths all at once, as if it sent out little clones of itself to check every possible route simultaneously. This idea is called non-determinism.
And you can see the difference right here in the formal rules. For our old machine, the DFA, a transition gives you exactly one next state, no choice. But for this new one, the NFA, a single input can lead to a whole set of possible next states. It's like it gets to explore a bunch of parallel universes with every single step.
And this is the first huge, mind-bending surprise in automata theory. You'd think that this superpower, being able to explore all these paths at once, would make the NFA way more powerful. But it doesn't. It turns out an NFA can't solve a single problem that a plain old DFA can't also solve. Even though they look totally different, their fundamental power is exactly the same.
And there's another way to describe this same level of power, and it's something you might have actually used before. regular expressions. Regex. They're just a super compact, kind of code-like way for us to write down the exact same patterns that our simple machines can recognize.
So let's nail this down. This is the crucial takeaway. Whether you use a DFA or the superpowered NFA or a regular expression, you are talking about the exact same class of problems. They're just different ways to look at the same thing. And we call this family of problems the regular languages.
Okay, now for what I think is the most interesting part. We know what these machines can do, but what about what they can't? What are their limits? Where do they break?
Check out this language. It's pretty straightforward. You have a bunch of A's, and then they're followed by the exact same number of B's. So, strings like AB, AAB, AABB, and so on. Seems simple enough, right?
Well, believe it or not, this simple little pattern is completely impossible for our finite automata to recognize. Why? Just think about it for a second. What would the machine need to be able to do to make sure the number of A's and B's actually match?
It has to count. It needs to count all the A's and then check off the B's one by one. But here's the fatal flaw we talked about earlier. Our machine only has a finite number of states. So what happens if you feed it a really, really long string of A's? Eventually, it's going to run out of new states, and it'll have to repeat one. It enters a loop, and the second it enters that loop, it loses the count. It has no idea if it saw 10 A's or 100. Its amnesia is its downfall.
But here's the thing. This limitation, this failure, it isn't a bug. It's actually a feature. It shows us that there's a beautiful structure to computation, almost like a ladder, where each new rung gives you more power.
And here it is. This is the Chomsky hierarchy, named after the linguist Noam Chomsky. It's that ladder of computational power. Our little finite automata and their regular languages, they're right down there at the bottom, on the first rung, type 3. They're the simplest class. To solve more complex problems, you've got to start climbing that ladder to more powerful machines.
So what's the secret to climbing the ladder? How do you get more power? It's all about giving the machine more tools. To solve a problem like matching A's and B's, our machine needs the one thing it's been missing this whole time: memory. And that's where we'll leave it, with a final, tantalizing question. Our machine failed because it had amnesia, because it couldn't count. So what happens when we finally cure it? What amazing new worlds of computation open up the second we give our machine even the simplest kind of memory, like a pad of paper to take notes on? Well, that's where the real power starts. And that's a story for next time.